Hi, gang. Welcome back. This is Geometry Section 2-6. And this is the last section in Chapter 2. And we've been talking about logic this whole chapter. But now we're going to start to analyze actual arguments. Not just statements, but a group of statements. Now, a group of statements, one statement and then another statement and then another statement, in a chain that follow each other logically, each statement is called a premise. Now, if you're using proper logic techniques, when you list off a few premises, if they match something that is logically valid, a logically valid argument, then the conclusion that you can draw, obviously it's called a conclusion, the conclusion that you can draw can be trusted to always be true in all cases. Now, when I took logic in college, we identified 32 different logic arguments that were valid. All right, and that goes clear back to the ancient Romans. They're the ones that studied this, and a lot of the names that we had to memorize for each type were in Latin. All right, but we're just going to use like English names, and we're only going to study two. Well, basically three. There are two on your note card, and I'm going to add one. Let me just talk a little bit about your note card. Here's what an argument, which is a set of premises and then a conclusion, looks like when you're using symbols. You know, you have a list of premises that or statements that you would use letters, the way we've been doing it with symbolic notation. And then when you get down to your conclusion, you draw a line. And what that does is that signifies that's the end of my premises. Therefore, now I have this conclusion. And we talked about these three dots meaning therefore. Now we're going to see them again. The first law, or the first valid argument that we're going to study, is called the law of detachment. All right? The law of detachment simply says if you ever have an if-then statement, a conditional statement, A implies B, or if A, then B, and we can all agree that that is true, and if we can all agree that A is true, the if part, whatever the if part is, in this case A, then we can validly conclude that B has to be true. All right, so if A implies B is true, and if A is true, therefore B has to be true. That is always the case when an argument is in this form, and that is called the law of detachment. Another one of the laws that you'll see used occasionally is called syllogism. Here's what syllogism looks like. If you have one if-then statement, one conditional statement, A implies B, and we can all agree that that's true, and if we can agree that it's true that B implies C, therefore it has to be true that A implies C. Now, we talked about this, only instead of the little arrow, we put equals in there. If A equals B, and if B equals C, then A has to equal C. Do you remember what property that was? That was the transitive property. You guys, syllogism is just the transitive property, only you're using if-then statements instead of mathematical statements. If A implies B and if B implies C, therefore A has to imply C. Now here's one that's not on your card. If a conditional statement, A implies B, is true, automatically it's contrapositive, has to be true. That's called the law of contrapositive. So therefore, not B has to imply not A. That has to be true. All right, that's an explanation of your note card. Now let's work a few problems. We are back, and we're going to work some problems from section 2-6. This is logic, and for a lot of students, this is the hardest thing about studying logic. Remember the three rules that we've talked about. Law of detachment, if A implies B, and you have A, therefore you have to have B. The law of syllogism, if A implies B, and if B implies C, then A has to imply C. And also the law of contrapositive, which says that if a statement is true as a premise, its contrapositive is also automatically true. Let's get down to business. They're going to give us some statements in words, and they're going to ask what we can conclude, if anything, based on the laws of logic that we've learned so far. This is valid reasoning. What I'm going to have to do is translate these into symbolic notation. Let's start with number 10 on your worksheet. Take down this example. It says, if George was not playing games, then it is raining. George was playing games. What can we conclude? All right, before you jump to any conclusions, let's put it into symbolic notation and see if it matches one of our three laws that we know are valid reasoning techniques. I'm going to do this in blue. Oh, got a marker. If George was not playing games, all right, we're going to call that P. It is raining. That's Q. Now let's write down this argument and see if it matches anything. If George was not playing games, then it is raining. That's P implies Q. Now the next statement is George was playing games. If P is he was not playing games, how do I symbolically show he was playing games? Isn't that just the opposite of P? Yeah, so that's this. There are our premises. P implies Q, and you have not P. Well, does that match any of our logic laws? Because law of detachment is close, but it's not exact. Law of detachment would say P implies Q, and you have P. You don't have not P. Okay? So this does not match. It does not work, and we can conclude nothing. There is no conclusion to be drawn from these premises. All right, that's probably tricky. Let's do another one. Let's look at number 12. If a project is due Wednesday, then Rebecca loves school. The project is due Wednesday. What can we conclude? Again, let's change it into symbolic notation. I'll use A and B this time. I could use X and Y or any letters I want. Let me use A and B. Project is due Wednesday. Let's call that A. Then Rebecca loves school. Call that B. The project is due Wednesday. Now, let's translate this to symbolic notation. If A, then B. Well, that's A implies B. How does this compare to A? The project is due Wednesday. That's exactly what A is. So A implies B, and we have A. Therefore, can we conclude something? Yeah, the law of detachment says you automatically have to conclude B. So what is our conclusion? B, and that is Rebecca loves school. So I'll write that down. Rebecca loves school. And really, who doesn't love school? All right. Now, number 17. This may be the hardest one because there are actually two steps. One of them they don't tell you, but it's kind of assumed. Let's talk about this one. If Kathy doesn't go to the store, then Denver went out Monday night. I didn't put night on there. I'm abbreviating here. If Ian goes to the store, then Denver did not go out Monday night. All right. Let us call Kathy doesn't go to the store P. Denver went out Monday. We'll call Q. Ian goes to the store. That's a whole other statement. All right? So we'll call that R. P, Q, and R. You can call it whatever letters you like. That's R. Then Denver did not go out. Well, what exactly is that? We already have one that said he did go out Monday night. That was Q. This must be not Q. All right, so now let's translate this argument into symbolic notation. Okay, the symbolic notation is this. Kathy doesn't go. If Kathy doesn't go to the store, that's P. Denver went out Monday night, that's Q. So we have P implies Q to begin with. If Ian goes to the store, that's R. Then Denver did not go out Monday. That's R implies, and that's just the opposite of he did go out Monday night, so that's not Q. All right, here's kind of the kicker on this one. We're going to make an assumption. If P implies Q is true, its contrapositive automatically has to be true. So I'm going to put its contrapositive as a premise. What's the contrapositive of P implies Q? Well, I not only take the if and the then and switch them around, but I negate both of them. So it's not Q implies, not P. Not Q implies not P. And now, if I look only at these two statements, one statement implied a second statement, and then the next step or premise was that second statement implied a third statement. What can I say about the first and the third? This is law of syllogism. Well, I can conclude now, therefore, R implies not P. That is a valid conclusion by law of syllogism. And I just have to write this out in words. What's R? Ian goes to the store. So I write if Ian goes to the store, then what? Not P. Well, P was Kathy doesn't go to the store. What's not P? That she does go to the store, right? So then Kathy goes to the store. There is a valid conclusion. If Ian goes to the store, then Kathy goes to the store. Keep in mind, if you got something a little bit different, it still may be correct. Because remember, whenever a conditional statement is true, its contrapositive is automatically true. What's the contrapositive of this conclusion? If Kathy does not go to the store, then Ian does not go to the store. That is also true. I think in the answers, that's what they got. If Kathy does not go to the store, then Ian does not go to the store. But since that is equivalent to saying this, either one of them is right. All right, that's section 2.6. Good luck on the problems, and we'll see you next time.